We need to talk about water because water is crazy weird. All right. Sorry. So water has this fun little thing. It's called auto ionization. Auto does it on its own. Ion makes charged particle of water, H2O. So if you think about two water molecules, you're gonna like this. You're gonna like this. All right, we'll be right back. If you think about two water molecules, they can actually run into each other and react in an equilibrium reaction, forming two different products, this hydroxide and this hydronium, which means water is another thing that we can say it's called amphoteric. It can be both an acid and a base, depending on who you put it with. Oh boy. Okay, here's what we got. I'm just going to pair them up. It doesn't matter who you buddy up with because ultimately you're going to end up with very similar pairings. If I pair up our two kind of reactants to products in this fashion, if I look at this first water and I say it's changing into hydroxide, well, that is giving away a hydrogen. We would say that by the Bronsted-Lowry definition, this water molecule is acting as an acid to form our conjugate base. I'm going to abbreviate here. It's CB, conjugate base, which makes sense. Hydroxide, that's like the base particle. Cool. This other water could accept that hydrogen to form this hydronium. So this is going to act as the base, accepting a hydrogen to turn into H3O plus, which is now your very much conjugate acid, the conjugate acid. Now, water doesn't do this very much. It just doesn't, right? We know water isn't an acid or a base, but we do know that in solution, there's some of this hydronium floating around because water actually has a pH. pH means powers of hydrogen, parez-vous de hydrogen, according to the original French. We actually have a way to measure the pH of water. It is 7. So some of the water molecules actually do this, not very much. It is very much an equilibrium. It goes back and forth between these two. Cool. There's that piece. Well, we can take it a step further. If this was our reaction, we could actually write an equilibrium expression for this. We could actually write products over reactants. We would end up with our hydroxide concentration. Sorry, let me get my little screen shield here. Nope. Come on, grab it. There we go. Times our hydronium concentration, H3O plus, all over our reactants, which would be H2O times H2O. Cool. Hopefully you're recognizing that this is a trap because this pure liquid does not get included. So we'd say that our equilibrium would just be our hydroxide times our hydronium. And we give this a special name. We call this KW because it is the equilibrium expression specifically for water, KW. And because most aqueous solutions have water, that's why we start the pH scale at 7, at neutral. And at that point, these two values are equal. For every two water molecules that have this little reaction occur, they change into one hydroxide and one hydronium. They are in equal concentration, which means we can actually have a constant for our water. We call this the autoionization of water. We call this Kw the ion product constant for water. Kw is a constant at 25 degrees. Like all other K values, it's a constant. It is equal to 1.0 times 10 to the negative 14th at 25 degrees. Always at 25 degrees, which is nice because that means that if you know the hydronium concentration, you can figure out the hydroxide concentration because you have this constant. More on this in here in just a second. We'll revisit this after we talk about how we do our pH calculations. Cool. Just as kind of some general notes here, a change in our hydronium will cause an inverse change in the hydroxide because if you have more hydronium, they're going to react with hydroxide, making less hydroxide. Oh, in an acidic solution, we have more hydroniums. We got more acid particles than hydroxide. And so our pH is less than 7. Hold that thought. In a basic solution, it's the reverse. You got more hydroxides than hydroniums. In neutral, they're equal. Kw equals those two times each other, and they will always equal 1 times 10 to the negative 14th. Our water, and here's a little vocab term for you. Water can be described as both an acid and a base. It's amphoteric. Amphibians, both land and sea. Both land and sea. Cool. Need to talk about our pH calculations. Let me pop up here for just a second. When we start to calculate pH, this is actually the basis for our pH calculations and how we start to get that pH scale. We say that if you got a pH of 7, you're neutral. If you're less than 7, you're acidic. If you're more than 7, you're alkaline or basic in nature. There's such a thing as a pOH scale. We don't use it very often, but that just is describing, if pH describes how acidic something is, pOH describes how basic that substance is, how alkaline it is. But it is comparing the opposite piece. You'll notice the number switch there. For the pOH scale, less than 7 is acidic and greater than 7 is, less than 7 is basic, greater than 7 is acidic. All that to say, usually we don't really use the pOH scale. We just use it to get back to the pH scale. And here's how we can do that. Turns out there is a mathematical way to do this. We have seen this once in, I think, Theo a long time ago, but it's worth revisiting. I'm going to throw all the equations up here, and then I'm going to kind of connect them. So if you're looking at this, there's a better way. There's kind of a square for this. So give me 1 second. But we can calculate directly for pH. It is the negative log of your hydronium concentration. It's just saying how concentrated are the acid particles. Sometimes it'll just be H+. You'll see that as just H+, so negative log of H+. They mean the same thing in an aqueous solution. If we're thinking about our concentrations, oftentimes they're really little, times 10 to the negative 14th, for example, for our Kw. These are small values, and they're kind of cumbersome. By changing it to a pH scale, we now have a whole number. It makes comparing acids and their reactivities a lot easier. And so that's where our pH scale comes in handy. If you want to know the pOH or how basic something is, it's negative log of the hydroxide. Oh, nice. Same math, different scale. But the two come together. If you take how acidic something is and add how basic it is, they will always equal the total of the scale, which is 14. So your pH plus your pOH will always equal 14. If you're going backwards, your hydroxide concentration is 10 to the power negative pOH. To go back from pH, it's 10 to the negative pH. It'll get you back to the hydronium concentration. And every now and then you'll see a pK or a pKa. That's just a negative log of the K, which is kind of again, just a bookkeeping thing that helps us compare numbers a little more easily if you see a pK or a pKa. Cool. So there's all these formulas. Let's condense it. Let's make it a little easier to navigate and kind of have them all in one spot. So let's look. I hit the button. Yeah, let's look at an example. I gotta disappear again for just a second. And I hit this button. Boop. Cool. All right. So usually we're looking at an acidic solution. And so we'd say, well, how acidic is it? What is your hydronium concentration? If it's a strong acid, it's just whatever the molarity is of the strong acid. We know for a strong acid, it dissociates 100% of the time. And so whatever your acid concentration is, that's your hydroxide or your hydronium concentration. If we wanted to go to pH, it is a logarithmic scale. We would take negative log of our concentration of our acid, H3O+. Now, again, we're assuming a strong acid. Weak acid, these rules get a little funky. That's coming up later. Cool. If you had a base, well, you wouldn't know the H+, you know the OH minus concentration for our strong base. If you wanted to go to the pOH, well, it's the same math, negative log of your hydroxide concentration. Cool. So it's the same math, just kind of how are you, or what substance are you describing, an acid or a base? Cool. If we're thinking about the math, we want to go backwards. I'm going to show the math real briefly. We know that pH equals negative log of the H plus or the H3O plus. Cool. If we wanted to work backwards, we'd have to multiply both sides by -1. That gets rid of it on this side. So now we have negative pH equals the log of our H plus. To get rid of the log, we do 10 to the power. 10 to the power. Now we got just our concentration. I just wanted to show it real quick for my math savvy folks, all you guys in these upper level math classes. All that to say, if you want to go backwards, from pH, oh, I want the pen. Where's my pen? If you're going to go backwards, it's going to be 10 to the power negative pH. If you were dealing with your base, same math, different numbers, different concentration, would be 10 to the power, 10 to the power negative pOH. So all the math here is just the same. Now we need some way to put these two together. Oh, okay. Well, a way to do that is the total of the scale. These two values added together plus the pH have to equal 14. 0.0. Oh, I've goofed that up. Sorry, let me get more space. Equals 14.00. Your pOH plus your pH have to equal 14. And this is on the logarithmic side. Oh, nice. If you're not in logarithm, it's your kW, 1.00 times 10 to the negative 14th. It's the same value. It's just what are you expressing it in a logarithmic scale, pH, pOH, or are you working directly in your concentrations? It's still your hydroxide concentration times your hydronium or your H plus concentration. So it is actually a cyclic structure. You could pick one direction and go all the way around, or you can just take the shorter path, whichever makes more sense to you. So it's the same formulas from that previous page, just kind of showing all the connections and how we start to tie it all back together. All I have to say, let's look at a couple examples here. So research chemist adds a measured amount of hydrochloric gas to pure water at 25 degrees and obtains a solution with a H3O plus concentration of 3.0 times 10 to the negative fourth. Calculate the OH minus. Is it neutral, acidic, or basic? Okay. We bubbled hydrochloric acid through the solution. It better be acidic, but more on that here in just a second, because usually we use our pH for that value. Let's kind of think about our math. There's two directions we can go based on our little square or our circle. The short way would be using kW. kW is just a number. It's always equal to your hydroxide concentration times your hydronium concentration. If we're thinking about what we know kW is just a number. It is 1.00 times 10 to the negative 14th. Negative 14th, sorry. We're trying to solve for the hydroxide concentration. So there's our X. We know the hydronium concentration was 3.0 times 10 to the negative fourth. Cool. So then to solve, I think we would divide over, let me grab my calculator. We would divide over that 3.0 times 10 to the negative fourth. So we're going to have 1 times 10 to the negative 14th divided by 3 times 10 to the negative fourth. And you get a value of X equals 3.3 times 10 to the negative 11th. And that is going to be molarity, brackets. What do we have more of? Acid or base particles in solution. Negative fourth is bigger than negative 11th. This is acidic. The other way we could find out is we could do the negative log of that 3.0 times 10 to the negative fourth. Because if we do the negative log of that value, we get the pH. Well, we get a pH of 3.5. Oh, 3.5. That's less than 7. That is also acidic. Theoretically, you could have gone pH, subtract from 14 to go to pOH, and then 10 to the negative that to get to OH minus, whichever direction you want to go, whatever makes the most sense. But here's how we start to use those values to actually solve for some substances or some materials. Some examples. Cool. Discard that. Blah, 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 blah. That's cool. Yep. Oh, look at that. Okay, cool. Let's try another one. I'm just going to run through the first scenario here just for example's sake, and then we'll kind of leave those other ones for you to try. I'll throw the answers up right here at the end of the video. So we got 3 molarities for HNO3. That is strong. Cool. So we actually know the H3O plus concentration will equal, for the first one, 2.0 molar. Because it's strong, it associates 100% of the time. So we already know, boom, check, got it. Because it splits completely. Here's our concentration for our nitric acid for the first one. Oh boy, cool. So we know our hydronium, if we want to solve for pH, it's going to be negative log of our hydronium. In this case, it's going to be 2.0. Oh my goodness, it's concentrated. It's going to overpower our water solution. Here we got a concentrated solution. I bet it comes out to be negative, which is a thing you can have. We don't have it happen very often, but it can occur. So I do negative log of that number. We get a pH of negative 0.0 or 0.30. Yes? Yes. Cool. Here's our pH. Cool. So pH, check. I'm going to skip hydroxide because I know I need pOH anyway, so I'm just going to keep going around my square. I know that pH plus my pOH has to equal 14.00. Coming back on class later this week, we'll talk about sig figs for the pH scale. You're not going to like it very much. Yeah, we'll talk about it in class. Cool. So we got 14. So if we want to solve for pOH, we would subtract. We know the pH was 0.30. So we're going to have 14.00 minus a negative 14.30 to get a 14.30 pOH. So we just subtract. We knew the pH, we subtracted over to get just the pOH. Cool. And last but not least, if we want to go back the other way to get just your OH minus concentration, that's going to be equal 10 to the power negative pOH. Oh my goodness, sorry, I'm getting sloppy. Let me zoom in here a little bit. Negative pOH, negative pOH. Cool, so we need 10 to the power negative 14.30. That's going to be really little. We got second function log negative 14.30, close parentheses. We get a hydroxide concentration of 5.0 times 10 to the negative 15th. Holy crap, that's tiny. Oh, we had a concentrated acid, which actually neutralized some of the base particles from the water, giving us a crazy small molar concentration of hydroxide in solution. Cool. So sorry, let me box all my answers here. We got hydroxide concentration and pOH. Cool. So here's our hydroxide. Here's our pOH. Sorry, this one got kind of messy. Here's our pH, and here's our hydronium concentration. Cool. Try the other ones. Let me clear this off. Erase all. Discard. Discard. Boop. Cool. So if we were actually going to work the other ones, we would do the same process for other values. For this one, we would end up with, for our 0.3 molar concentration, we end up with 0.3 molar and 0.52 for the pH. Get a hydroxide concentration of 10 to the negative 14th divided by 0.3 to get our 3.3 times 10 to the negative 14th molar, pOH of 13.48. And for a really dilute one, we end up with a pH of 2.20 and our pOH 11.80. Again, these two values added together have to equal 14. Nice little built-in double check depending on which direction around the square you're going. Cool. Hopefully you're feeling okay on our pH calculations. There's some practice on our homework sheet. Feel free to be trying those. We'll be coming back and checking those when we get back together. Awesome. Keep on, keep it on.